This video is about the binary logistic regression. Recall that in linear regression, we have this equation, and we are using linear regression whenever y is a continuous variable, meaning it is a quantitative variable that allows decimal values. Meaning we are using linear regression whenever this dependent variable y is numerical in form, specifically a continuous variable, meaning decimals are allowed. However, in binary logistic regression, this y is now a binary variable, meaning a categorical variable with only two outcomes. A binary logistic regression is called a logistic regression since it's using a logistic function that models the probability that y equals 1, in which further, this equation leads to this form, wherein the left side refers to the ln of the odds, and then the right side of the equation is just like the linear regression. Now, since the left side of the equation is naturally binary, this part of the equation, which is called as the log-link function, makes the left side of the equation continuous, meaning decimals are allowed already. Now, let's start with the simple binary logistic regression, which is also called as the univariate binary logistic regression, in which we only have one predictor, which is x sub 1. Now, let's try to open the file, pharyngealC.RData. Now, we can see that the file contains three essential columns, which are the pharyngeal cancer, in which 1 was coded as positive and 0 was coded negative. Another column, which is smoker, whether the patient is a smoker, which is 1, or non-smoker, which is 0. And then age, which is expressed in years. We may see the structure of the file using str pharyngealC. Now, let's create a cross-tabulation using the table function. And we can see this cross-tabulation table. Now, suppose you're asked to find the odds ratio of having pharyngeal cancer for smokers versus non-smokers. So, using this table, wherein it's like having pharyngeal cancer as positive and negative, and whether smoker or not. We see that this table shows us that there are 47 cancer patients who are smoker, 52 cancer patients who are non-smokers, 79 patients who are negative of pharyngeal cancer but are smokers, and 162 non-smokers who are negative of pharyngeal cancer. Now, computing for the odds ratio, remember that odds ratio is A over B divided by C over D. So, computing for that, since this is A, this is B, this is C, and this is D, we're going to have 47 over 52 all over 79 over 162, which gives us an odd ratio of 1.853, which indicates that the odds of having pharyngeal cancer is 1.853 times to smokers versus non-smokers. Now, let us see later if we can get this same value for the odds ratio using the binary logistic regression. Now, let's perform the binary logistic regression using this code. Now, this code uses the GLM function, which stands for General Linear Model, since the binary logistic is one of the general linear models in statistics. This one is our dependent variable y, and this one is our independent variable. In this case, we have x sub 1. Now, we have to declare that the family is binomial, meaning we're going to make use of a binary logistic regression using the log-link function given the data, which is pharyngealC. And we're going to see these results, in which this shows that the ln of the odds of having pharyngeal cancer is equal to beta sub 0, which is negative 1.1364, plus beta sub 1, this is our beta sub 1, 0.6171, times x sub 1, in which x sub 1 is 1 if smoker and 0 if not. Now, let's compute for the ln of odds for smokers. Meaning, let's substitute x sub 1 as 1. What will happen? So this part will just be equal to 1, giving us a value which is negative 0.5193, in which negative 0.5193 is the ln of the odds of having pharyngeal cancer if smoking. Now let's try computing for the ln of the odds for non-smokers, meaning x sub 1 will be 0. So this part will now be 0. So substituting x sub 1 as 0, we're going to have negative 1.1364. If we're going to subtract this value to this value, meaning the ln of odds when x is 1 minus the ln of the odds when x is 0. So this value minus this value, we're going to have 0.6171, which is the coefficient for smokers here, as given by R. So what does this indicate? That indicates that the log of the odds, which is this one, or the ln of the odds of having pharyngeal cancer is 0.6171 higher for smokers as compared to non-smokers. So again, this one refers to the increase in the ln of the odds for smokers versus non-smokers. Now, in algebra, we know that the log of A minus log of B having the same base, when we speak of ln, that is just the log at base E. So log of A at base E and log of B at base E, or in other words, the ln of A minus the ln of B is just the same as the ln or the log of A over B. Thus, we may express this left side of the equation is like this is your A and this is your B. So ln of A minus ln of B may be expressed as ln of A over B. In other words, this left side may be expressed as the ln of the odds when x is equal to 1 over the odds when x is 0, which is equal to 0.6171. Now note that since we are dividing odds here, that is the odds ratio. In other words, the ln of the odds ratio is 0.6171. Now, if we need the odds ratio, we know that the ln, let's say, of A is equal to B, meaning the log of A at base E is equal to B, is like saying that E raised to B is equal to A. Meaning, this part tells us that E raised to 0.6171 is equal to the odds ratio because of this, thus giving us an odds ratio of 1.854, which is exactly the same as the odds ratio when we computed for the odds ratio using A over B all over C over D a while ago. Thus, this tells us that the odds of having pharyngeal cancer is E raised to this, or in other words, 1.854 times when exposed to smoking compared to when not exposed. So the question is, how are we going to get 1.854 using R if this is just the exponent of the Euler constant E? Now, to get 1.854 using R, all we have to do is to use the exp function. So exp, and then we're going to get the coefficients from the pharyn log mod 1 result. And at the same time, this conf_inf gives us later the confidence interval for the odds ratio. Again, using the result coming from pharyn log mod 1. If you want the odds ratio or the result to be rounded off in 3 decimals, we may use the round function and then comma 3 outside the exp function. So R gives us these values, wherein this one is the odds ratio and this one is the 95% confidence interval for the odds ratio. Now note that since the p-value here is less than 0.05, the odds ratio does not include 1, as we can see here. So this tells us that the odds of having pharyngeal cancer is 1.853 times when exposed to smoking compared to when not exposed. and then this is the 95% confidence interval. Now, let's perform another univariate binary logistic regression. This time, we're going to make use of age as our x sub 1. Now, using the same file, pharyngeal.RData, let's just replace smoker with age. And we're going to make use of pharynlog mod 2. By the way, this part, you may modify it if you want. It's up to you. It's just the name of the object. Now, doing that in R, and we're going to have this result. Now, this tells us that the equation we have is now the ln of the odds of having pharyngeal cancer is beta sub 0, which is negative 2.797244, plus beta 1 times age, in which age is expressed in years. Now, let's compute for the ln of the odds of having pharyngeal cancer of, let's say, a 50-year-old patient. So, meaning x sub 1 here will be equal to 50. And computing for the ln of the odds, we have negative 0.640794. Now, let's try to increase the age by 1, meaning a patient who is 51 years old. So, replacing x sub 1 with 51, we're going to have negative 0.597665. Now, what does this result tell us? If I'm going to subtract the ln of the odds for 51 years old minus the ln of the odds for 50 years old, we're going to have 0.043129, which is the one given by R. Meaning, this value tells us that for 1 unit increase in age, the ln of the odds increases by 0.041329. Now, performing what we had a while ago, if I'm going to make use that ln of A minus ln of B is the same as ln of A over B, meaning if this is your A and this is your B, that will result to, which is equal to 0.043129. In other words, the ln of the odds ratio here, comparing 50 and 51 years old, I'm still going to have 0.043129. Meaning, if I'm going to get the odds ratio, which is exponential of 0.04, I'm going to have 1.044. Now, what does that 1.044 mean? Let's try another one. This time, let's have, let's say, 51 versus 52 years old. So, for 51, I'm going to use 51 as x sub 1. I'm going to have the same answer a while ago. And for age 52, I'm going to use x sub 1 as 52. I'm going to have this. Now, subtracting the ln of odds for 52 years old minus 51 years old, I'm still going to have 0.043. It's because, again, this one states that for every 1 unit increase in age, the ln of the odds increases by 0.043. So if I'm going to compute, let's say, for the ln of the odds when x is 60 and ln of the odds when x is 61, subtracting those ln, I'm still going to have this value. So in other words, I'm still going to get the same odds ratio, which is 1.044. As long as I'm increasing the age or x sub 1 by 1. Now, what if this time I'm going to increase the age by 2? Meaning, I'm going to compare the ln of the odds for 50 versus 52 years old. So, I'm going to have the ln of the odds as negative 0.64 when x sub 1 is 50. And when x sub 1 is 52, I'm going to have negative 0.55. Now, this time, instead of subtracting those two ln of odds, let's try now this time. I'm going to divide those two ln of odds. So, the ln of odds when x is 52 is this one, divided by the ln of the odds when x is 50, which is this one. Now, since the ln of the odds is equal to this, I may compute for the odds. Again, since ln of the odds is negative 0.554, meaning the log of the odds at base E is negative 0.554. So if I want to compute for the odds, I will just have E raised to negative 0.554. That gives me the odds when X is 52, which is this one. Likewise, when X is 50, I'm going to have this one. Now, dividing this 2, we're going to have an odds ratio. Since I divided the odds over the odds, that odds ratio is 1.09008. This time, the odds ratio here used 50 and 52. Meaning, the odds of having pharyngeal cancer is 1.09 times for a patient age 52 versus a patient age 50. Now, this 1.09 here is actually the square of 1.044. Meaning, the odds of having pharyngeal cancer increases by a factor, meaning this one, for every 1 year increase in age. Now, this tells us that, for example, I'm going to compare the odds of having pharyngeal cancer when age is 65 and when age is 60. What I'm going to do is just 1.044 raised to 5, since the difference here is 5. So that is what we mean by this a factor of. Again, 1 year increase means 1.044 raised to 1 increase. A 2-year increase means 1.044 squared increase in the odds. And let's say 5-year increase means 1.044 raised to 5 increase in the odds. So if you want to see 1.044 instead of 0.04 in the result of R, all you have to do again is to use the EXP, meaning the exponential of 0.043129, expect that that is equal to 1.04. So this one is the odds ratio and this one is the 95% confidence interval of the odds ratio. And note again that since this p-value is less than 0.05, that's why the odds ratio does not contain 1.0. So this tells us that for every 1 year increase in age, the odds of having pharyngeal cancer increases by a factor of 1.044. Now, let's use the same data, pharyngealC.RData, in performing a multiple binary logistic regression, wherein we now have 1, 2, up to p predictors of y, in which y again is a categorical variables with 2 outcomes. Now, note that this is the result when using a univariate binary logistic regression with smoker as a predictor. This was our result a while ago. And when age is a predictor, we have this result. Now this time, let's combine smoker and age in one model, meaning I'm going to make use now of age as x sub 1 and x sub 2 as smoker. So in other words, in the model, all we have to do is smoker plus age, and let's name it as pharynlog mod 3. Then likewise, let's use the summary function and eventually the exponential function for the odds ratio. So we're going to have this result. Now what you must remember is that when performing a multivariate logistic regression, it's better if you make use of the univariate first. Why? It's because we want to see the independence of the predictors. In other words, the values here using the multivariate binary logistic regression must be very near to the value using the univariate logistic regression. So notice here that this value and this value are very near to each other, and likewise this value and this value are very near to each other, which tells us that using smoker and the additional of age in the model did not change this odds ratio dramatically. So that indicates that smoker and age are independent with each other. So using this result, we may create a table. So this one using the univariate with this as odds ratio 1.85 and 1.04 for age. And then these are the confidence interval for smoker and this one for age. Now this one is the multivariate results, meaning 1.816 or 1.82 and 1.043 this one. And these are the confidence interval displayed here. Now some call this odds ratio as the crude odds ratio, which is the odds ratio using the univariate. So in other words, if you have a categorical predictor, the crude odds ratio is the one which is A over B over C over D. And then this one, some call this as the adjusted odds ratio. So again, the odds ratio produced by the multivariate must not be very far with the one that is produced by the univariate binary logistic regression. Now, to interpret this or how to write up the result, all we have to do is to take a look at the multivariate regression results. So this tells us that there's sufficient evidence that smoking, so this is 0.018, and age, which is the p-value here, are the risk factors in developing pharyngeal cancer. Keeping other variables constant, since again, we're making use of a multiple regression model, the odds that pharyngeal cancer develop due to exposure to smoking is 82% more, or in other words, is 1.82 times compared to non-exposure to smoking. And then in addition, every 1 year increase in age, the odds of developing pharyngeal cancer increases by a factor of 1.04, which is the one displayed here. And then the confidence interval. Let's have another example, which is PapillaryTumor.RData, wherein this is about an oncologist who is interested to determine the factors that lead to papillary tumor growth, which are cancerous cells which are found in the throat. Data from 40 patients who may have lived with exposure to radioactive iodine in the last 5 years and those who have had thyroiditis in the last 6 months were recorded. We're going to create a logistic regression model that identifies the factors that lead to papillary tumor growth using 5% level of significance. So we may open the file, the PapillaryTumor.RData. So here we see 80 patients in which their nuclear location, gender, papillary tumor, thyroiditis, mild X-ray, high X-ray, and family history were recorded. So the nuclear location here tells the distance in kilometers of the nuclear plant from the residence of the patient. So for example, patient number 1 here, who is living 2.6 kilometers away from the nuclear plant, gender's male, he has papillary tumor, he have had thyroiditis in the last 6 months, no exposure to mild X-ray in the last 2 years, but with exposure to high X-ray in the last 2 years and with no family history. Patient number 9, for example, is living in a residence which is 5.65 kilometers away from the nuclear plant, gender's female, positive of papillary tumor, no thyroiditis in the last 6 months, but with exposure to mild and high X-ray in the last 2 years and with family history of papillary tumor. So note that the dependent variable here is the papillary tumor. So this one is our Y. The rest are X. So we're going to make use of the GLM function in which the dependent variable is papillary tumor. And then we're going to have the independent variables such as nuclear location, gender, to family history. And then we're going to make use of the family, which is binomial, and then the link function, and then the file name. So we're going to have these results. So we can see here that nuclear location, gender, and exposure to high X-ray in the last 2 years are the predictors of developing papillary tumor. So again, all we have to take a look are the ones with the p-values less than 0.05. Now, to display the odds, we're going to make use again of the exp function. We may round it off to 3 decimals. And we're going to have these results. So again, this tells us that nuclear location, gender, and exposure to high X-ray in the last 2 years are the predictors of papillary tumor growth. Now note here that R displays the label where 1 is recorded. Consider that gender is coded as 1 and 0. 1 means male and 0 means female. So male is displayed right after the variable name. Likewise, for the mild X-ray and high X-ray, 1 is coded as yes if the patient has exposure to mild X-ray or high X-ray in the last 2 years, while 0 if not. That's why yes is right after the variable name here. It makes us easier to interpret the odds ratio. Like for example, if we're going to interpret 7.55, this tells us that the odds of developing papillary tumor is 7.55 times for those with exposure to high X-ray in the last 2 years compared to those who do not have exposure to high X-ray in the last 2 years. Likewise, this 8.59 tells us that the odds of developing papillary tumor is 8.59 times for males compared to females. Now, for 0.75, since nuclear location is a numerical variable, so this tells us that 1 kilometer increase in the nuclear location, meaning for every 1 kilometer that the house is far from the nuclear plant, the odds of developing papillary tumor increases by a factor of 0.75. What does this tells us? Meaning if the house or the residence is 2 kilometers away, so this will be the odds. If the odds is 3 kilometers away, this is the odds. Notice here that this will just decrease as the exponent gets larger. Because as we know, 0.75 raised to 3 is lower as compared to 0.75 raised to 2. That's why for every 1 kilometer increase, the odds increases by a factor of 0.75. Again, it tells us that the odds decreases for every 1 kilometer increase in the nuclear location. So, to have a sample write-up, so keeping other variables constant, again, we have to make use of this since this is a multiple regression model. The odds of developing papillary tumor is 8.59 times in males as compared to females or women. And then the odds of developing papillary tumor is 7.55 times for those with exposure to high X-ray in the last 2 years compared to those without exposure of high X-ray in the last 2 years. Then again, for every 1 kilometer increase in the nuclear location from the patient's residence, the odds of having papillary tumor increases by a factor of 0.75. Which again tells us that the odds decreases for every 1 kilometer increase. And then moreover, it tells us that having thyroiditis in the last 6 months, having exposure of mild X-ray in the last 2 years, and having family history do not lead or do not contribute or not predictors of papillary tumor growth. Next, let's have the RenalCast.RData. This is about a group of researchers who wanted to determine the variables that leads to renal cast formation. So our dependent variable here is the renal cast. So as we can see, this is coded as 1 if present and 0 if not. The years of occupation, if painting is included in the occupation, and urinary findings such as BUN, the uric acid, the pH, and whether there is a bacteria in the urine were recorded. So note that painter and bacteria are also categorical variable. So 1 here means painting is included being a construction worker and 0 if not. In the bacteria, 1 here tells us that there is a bacteria in the urine and 0 if not. So let's proceed. So we're going to make use of, again, the GLM function with y comes first. So in other words, we're going to make use of renal cast and then the independent variables such as the occupation years plus painter up to plus bacteria. So this tells us that occupation years and painter are the predictors or the risk factors that lead formation of renal cast. Then, keeping other variables constant, the odds of developing renal cast is 71.4 times if painting is included as construction workers compared to if not. And for every 1 year increase in the occupation being construction worker, the odds of developing renal cast increases by a factor of 1.23. And then these are their confidence intervals. The rest of the variables such as BUN, uric acid, pH, and bacteria are not predictors or do not lead to formation of renal cast. Now, I'm going to show you one study where it performed the binary logistic regression to show the factors associated with tobacco use. So, meaning the data here is like having Y as tobacco use. So, 1 means yes and 0 means no. And then, the other variables are, let's say, age group. Now, age group here is not in numerical form, but since they are in brackets, it's like having age group, let's say 15 to 19, let's say this is coded as 1, then 20 to 24 is coded as 2, 25 to 30, let's say is coded as 3. So since this is a categorical variables with more than 2 outcomes, there was a need of having dummy variables. So in performing the logistic regression, it's like having Y, which is tobacco use, then 1 and 0, and then it has age group, let's say age group of 15 to 19 as one dummy variable, age group of let's say 20 to 24 as having another dummy variable, then age group let's say of 25 to 30 as another dummy variable. And then one served as a reference, so it was removed. So, leaving these other dummy variables as the possible predictors. Now, since this serve as a reference, in the table, the odds ratio displayed is 1. So, whenever you see a research having an odds ratio of 1 among the dummy variables, that means that that variable is the reference variable. So, to interpret, let's say, one odds ratio, let's say 4.7, it tells us that the odds of tobacco use among 25 to 29-year-old individuals is 4.7 times as compared to the reference, which is 15 to 19 years old. Another one, for example, 10.7. This indicates that the odds of tobacco use of 45 to 49-year-old individuals is 10.7 times compared to 15 to 19-year-olds. Then for example, this one, 7.3, this tells us that the odds of tobacco use among 40 to 44-year-old individuals is 7.3 times compared to 15 to 19-year-olds. And then for the gender or sex, 13.1 here indicates that the odds of tobacco use among males is 13.1 times compared to females. Okay, so that's how you interpret odds ratio when there is a dummy variable. So another one, for example, this one, 1.7, this indicates that the odds of tobacco use among formerly married individuals is 1.7 times compared to currently not married or those who are single. Then for example, this tells us that the odds of tobacco use is 2.8 times among Muslims compared to one which is Orthodox. Another one, for example, 1.4. So this tells us that the odds of tobacco use among those in the poorer wealth index is 1.4 times compared to those among in the richest wealth index. Then this one did not use a p-value but rather a confidence interval. So this tells us that since the confidence interval here for the odds ratio does not include 1, rest assured that the p-value of this is less than 0.05. Like this one and this one. However, for those which includes 1, like this one, so this tells us that the p-value is greater than 0.05 since 1.0 is included in the confidence interval. So likewise, this one has a p-value greater than 0.05. And then moreover, since as you can see, this one uses the crude OR and this one is the adjusted OR, this tells us that this column used a univariate binary logistic regression while this one is generated using a multivariate binary logistic regression model.